spend some time looking at each of the effects and trying to see if this makes sense to you. Why would each division want to do this certain thing on an organ? So for instance, the pupil's eye, for the sympathetic system, you dilate your iris, but the parasympathetic response is you constrict them, you kind of make the pupil smaller, right? Why does that make sense? Why would you want to dilate your eyes in a sympathetic response?
The lights went out, it got dark.
Yeah, so you can see more things. So if you have more light going into your eye, you're gonna see more things. You'll be more vigilant, right? But then a parasympathetic response, you probably want to rest. You don't want to be, burdened with all the light and scenery around you, right? Yes.
For the digestive tract, it says decreases mobility or increases mobility. Is that
That's motility,
Oh.
but yeah. But it's a similar thing. The idea is motility and secretion is these, the GI tract's putting out enzymes, putting out mucus, right? And motility is how fast or slow your food is traveling through your GI tract.
Okay.
And so, since you brought that up, right, you don't want food to be digested while you're running away from a snake, right? Because that's energy expense. You would rather devote that energy and that blood supply to your muscles, not to digesting food. But when you're resting and relaxing, it's a good time to digest your food, and that's when they'll increase motility, increase secretion of your glands, right? And so, yeah, just look through each of these. This is like what's one of the two tables, and try to make sense of this. See if you can decipher why one system would do a certain response over the other system. Alright, so let's look at these postganglionic neurons and how they are affecting their target tissue. So here in this example, we have smooth muscle. So we can say the smooth muscle is surrounding a blood vessel. So if they start contracting, they're going to constrict that blood vessel, and if they're not contracting, they're going to dilate it. And so along this axon where this axon interfaces with the muscle, it has these kind of bulges along the axon. And these bulges are called varicosities. I'll spell it out bigger here if you can't see that. Varicosities. And so these varicosities act kind of like axon terminals. Remember back when we talked about synapses and we talked about axon terminals and how they release neurotransmitters? In the autonomic system, instead of using axon terminals, you use these varicosities. And so in this way, neurons can affect a large area of tissue without having a whole bunch of axon terminals. So along the length of this axon, if you can have these varicosities that release the neurotransmitter, you can affect much larger areas than having, an axon terminal synapse every single muscle cell. Yes?
This is how it's released in both the sympathetic and the parasympathetic?
Mm-hmm. Yep. So this is general to both, just the autonomic nervous system in general.
Okay, thank you.
And so let's kind of go over the process, how these varicosities release their neurotransmitter. And you'll see it's very similar to what happens at the axon terminal. So here we have our varicosity here, and we see here we have our action potential kind of come down the axon. And when it does, it's going to basically induce an opening of calcium channels. So calcium will then rush into our varicosity, just like an axon terminal. And then that calcium will induce the vesicles inside the varicosity that have been holding the neurotransmitter to then do exocytosis and release their content. And so they're releasing norepinephrine. So is this parasympathetic or sympathetic? This is sympathetic. And so here, this area you can kind of think as kind of like a synapse here. This is not a real synapse, I'll tell you that. In order to have a real synapse, you need to have an axon terminals, and you need to have some cell to interface with. This is not that. So that's why I put it in quotation. This is not a real synapse, but it acts a lot like a synapse. So what happens is, in normal process, norepinephrine will bind to its receptor, its adrenergic receptor. It will create a response here, and then that norepinephrine will then get released, right? We have to terminate that signal. So either it can diffuse away, find its way into blood vessels. It can be transported back transport back into the varicosity, so it can be reused as a neurotransmitter, or it will then be degraded by the mitochondria to be made into other stuff. In this situation, if it's norepinephrine, it can be degraded to make monoamine oxidase, which is used for some other metabolic process. But the whole point of this was just to show you that it works very similar to a synapse here. This calcium release, there are vesicles that get released, and the termination process works the same. But these varicosities can be chained together within one axon. So one axon, one postganglionic axon, can release neurotransmitters to a whole range, whole area of smooth muscles, for instance, or some other gland or tissue. There are some special cases of the autonomic nervous system, and this one is one of them. This is the adrenal medulla. So the adrenal medulla, just to code the name, that the medulla is inside the core. So this is the core of the adrenal gland, and it works differently than most other parts of the autonomic nervous system. So the autonomic nervous system primarily works off neurons, right? Neurons releasing neurotransmitters that excite either other neurons, the postganglionic neuron, or some kind of target tissue, muscle, organ, muscle gland, something like that, right? But this works a little differently, in the sense that there is a preganglionic sympathetic neuron. Keep in mind that this case of the adrenal medulla is only happening in the sympathetic nervous system. Its preganglionic neuron will go straight to the adrenal medulla. There is no postganglionic neuron. In this case, this preganglionic sympathetic neuron will then activate the adrenal medulla to create epinephrine. And then that epinephrine will then be released into the blood vessels, and then it'll circulate in the circulatory system, and then that epinephrine is how it will target various tissues. So it'll target heart, blood vessels, various other parts of the body to create another sympathetic response. And so this is an example where the sympathetic nervous system is now using a hormone to create its response. So not every response in the autonomic system is carried out directly by neurons. Sometimes you can have a hormonal effect, like with this epinephrine, to create the sympathetic response. And of course, this is a short-lived response. The half-life of epinephrine are within the minute scale. So this is not like a long-lasting hormone, but this is still, nevertheless, a hormone that's traveling through your bloodstream. Yes?
Are the receptors in the adrenal medulla nicotinic, or are they the one that starts the
They're going to be muscarinic.
muscarinic
Mm-hmm.
inside?
Yep. No, sorry, they're not muscarinic. Sorry, I take that back. They're nicotinic. Sorry, nicotinic. Okay.
So what is the chromatin cell?
So the chromatin cells are basically modified postganglionic cells. I didn't want to really get into that detail, but chromatin are cells that basically act like postganglionic neurons, but what they do is they essentially just release. They act like a neurohormone. They act like a neuron that basically releases a neurohormone. In that situation, the neurohormone is epinephrine, adrenaline.
And that goes straight into the blood vessels.
Yeah, so epinephrine is, you can consider it a steroid hormone. So it just, no, sorry, it's not a steroid hormone, but it acts like a steroid hormone because the catecholamine, and so it will diffuse through stuff because it's pretty nonpolar. It can get past cell membranes, and so it'll just diffuse into the blood vessels and get into the bloodstream. All right. So this diagram is just highlighting what we've been talking about, the autonomic pathways here. So we have our parasympathetic pathway here. We have two two neurons, a pre-ganglionic neuron and a post-ganglionic neuron. They synapse together at a ganglion, and then the post-ganglionic neuron can affect some target, whether it's smooth muscle, cardiac muscle, some kind of gland here, or sometimes even adipose tissue. And then you see the exact same thing with the sympathetic parasystem. Wow, the sympathetic pathway, where you have two neurons, they synapse at ganglion, and they have the same kind of pathway, same kind of structure, but they're releasing different neurotransmitters, right? So whether it could be either epinephrine or norepinephrine. And then here's our special case, adrenal sympathetic pathway. But it's more or less doing the same thing here, creating various effects at our organs. Now, to try to transition us from a kind of autonomic pathway to a somatic pathway, to try to lead us into talking about muscles, which we'll talk about Thursday and the coming Tuesday, this is what a somatic motor pathway looks like. It's just one neuron. You don't have to have, there's not two neurons in series, there's no ganglion here. It's just one neuron that travels from the central nervous system straight to the muscle. In this situation, okay, somatic, it's a skeletal muscle. And we'll talk about the differences in muscles later, when we talk about muscles and talk about the cardiac system. But somatic motor pathways usually will go to the skeletal muscle, and a lot, kind of like parasympathetic pathways, they release acetylcholine to affect these muscles. And they have nicotinic receptors. And so this is kind of what it looks like at where by the way, this neuron will be called a motor neuron.